2018 Higher Physics Section 2 Question 1, and it's a projectile question. During a school fun fair, a student throws a wet sponge at a teacher. The sponge is thrown with an initial velocity of 7.4 meters per second at an angle 30 degrees to the horizontal. The sponge leaves the student's hand at a height of 1.5 meters above the ground, and you're shown a diagram which is not to scale. Take a wee while to get used to the diagram, to get a feel what's going on, and then you can swing into your autopilot, your well-rehearsed mode. You know the first thing they're going to ask you is find the horizontal and vertical components of that initial velocity vector. So you should have this well and truly remembered. The velocity vector can be broken down into two components, a horizontal component and a vertical component, and they're related trigonometrically by this here. The vertical component is v times sine theta, and the horizontal component is v times cos theta, and you get that from the trig from that triangle. So the first question is finding the horizontal component. It couldn't be any more straightforward. All you have to do is find the horizontal component part, and that's vh, which we'll write down as VH, and that's going to be equal to V times cos theta degrees. I always try to remember, because it's the horizontal component that is on the ground, and the cos has got an O in it, so we say O on the ground. It's a quick way to remember it. Stick in the numbers. So V is going to be 7.4, the magnitude of the initial velocity vector, multiplied by cos of the angle cos 30 degrees. You put that into your calculator and you get an answer of 6.4 meters per second. And that's going to be the horizontal component of the vector. And I like to draw a wee arrow there to show you that's going to be the horizontal component, so as we can go back and think about it. The second question is much the same. We have to find the vertical component, and we know the rule. The vertical component size is going to be equal to V multiplied by, in this case, sine theta. So we put in the numbers. V is going to be 7.4 meters per second, and sine of 30 degrees. Okay, work that out in your calculator, and we have an answer of 3.7 meters per second. And remember, that's the vertical component, which means the arrow will be pointing up the way the component is up the way. So 2 marks right away. We've started the second section of the higher. Question 1A, part 2. Calculate the time taken for the sponge to reach its maximum height. Now, to do these type of problems in projectiles, we know we must completely rely on our template, and at the top of the template is our vectors of what is happening. You can see we have a velocity vector of 7.4 meters per second at an angle of 30 degrees, and we've broken that down into two components. Its horizontal component, 6.4 meters per second, and its vertical component, 3.7 meters per second. And you must be completely confident by working out what we call the projectile template, and that's it there written out for you. We can see we have a vertical column and a horizontal column. The vertical column has everything to do with the vertical components and all the vertical data. U is the initial vertical velocity of the projectile. V is its final velocity, any way we want to look at. A is the acceleration which the projectile undergoes, which we know is the acceleration due to the force of gravity. S is displacement, and T is the time at any particular part in that flight. The horizontal data I've written in words. Horizontal distance equals horizontal speed times time, because the horizontal speed component doesn't change through the flight, and we can split these two components up because they are independent of each other. Now let's go and put in the data. First thing, the initial vertical velocity. Well, initial vertical velocity we know is 3.7 meters per second, so that goes into the data. 3.7 meters per second. Now, what will be the velocity, the vertical velocity at the maximum height? Now, we know the vertical velocity at the maximum height is always got to be 0. So the vertical velocity at the maximum height is 0 meters per second. That's something you have to know and have to learn. The acceleration is our old friend, acceleration due to the force of gravity, 9.8 meters per second every second. S is the displacement from the starting point, and t is the time we're looking at, and that's what we're going to try and find out. We're going to try and find out the time it takes to get to that maximum point. Note, I don't need to use any of the horizontal data because I'm just interested in the time it takes to get to the maximum height. So what we got in our data? We have the initial vertical velocity, we have the final vertical velocity, we have acceleration, and we have to find time. So that means we're going to use this equation here. V equals u plus at. Now you have to be very adept, that means very good, at rearranging that equation to find out what time is. V minus u, if we take the u over the other side, and I always want to put it into brackets to keep it tidy, that's going to equal to at. So we divide by the acceleration, we have the time. V minus u divided by the acceleration is going to give us the time. Now all we have to do is plug in the numbers. Our final velocity is going to be 0. Our initial vertical velocity was 3.7, so that goes in. Put it in brackets. And we're dividing that by minus 9.8. Do that in your calculator and you get a time of 0.38 seconds. So that projectile took 0.38 seconds to get to its maximum height. Part 3 of question 1a. The sponge takes a further 0.45 seconds to travel from its maximum height until it hits the teacher. Determine the height h above the ground at which the sponge hits the teacher. Now we know from a previous question that the time taken for the sponge to go from the start to the top is going to be 0.38 seconds. So we know that's that time there. And we're told in this question that it's going to take a further 0.45 seconds to strike the teacher. So the total time from the moment it's launched until it strikes the teacher is going to give us a total time of 0.38 seconds plus 0.45 seconds, which has got to be 0.83 seconds. So we know the time it takes for the sponge from its launch until it hits the teacher is 0.83 seconds. Now all we have to do now is find the vertical displacement of the sponge at that particular time in its flight. To do that we must concentrate on the vertical data column in our template, and I'll mark that down to remind us. U, the initial vertical velocity, V, the vertical velocity at that particular time, A, the acceleration, which we know is acceleration due to the force of gravity, and we know S is the vertical displacement, which we're going to be looking for, and T will be the time at that particular moment. So filling in the data, U equals 3.7 meters per second. That's the initial vertical velocity. We don't know the velocity at that particular time, so we have to move on from that, leave it blank. We do know the acceleration is acting downwards, that's why we have to put the minus sign on it to give us minus 9.8 meters per second per second. And we're trying to find the vertical displacement S at the time t equal to 0.83 seconds. So we've got all our data lined up. We have got U, we've got A, we've got S, and we have got T. So we go and look up our data book, and the equation which is going to be used, the kinematic equation, will be S equals UT plus 1/2 of AT squared. Now you can see that we can just simply plug in the numbers because we don't need to do any rearranging. So S, the displacement at that particular time, we'll use brackets to keep it tidy for a calculator, is 3.7 multiplied by 0.83 plus, we'll change the half into 0.5 for a decimal for our calculator, multiplied by minus 9.8 since the acceleration of gravity is acting downwards, and we have to multiply that by 0.83 squared since that's in the equation. Plug that into your calculator and we end up with an answer of minus 0.30 metres. Now at this particular stage you might be thinking you've done the calculation wrong. Why should I get a minus displacement? But remember, you can get a minus displacement. That just tells us that the displacement is going to be downwards from the starting point. You see, if I draw a line from the starting point across here, if I take this dotted line here, that's zero displacement. And if I draw the line right across the way until it's well past the teacher, you can see from the diagram that if the sponge in this position, that's its maximum height above this line here. And you can see when it crosses this line here, its this vertical displacement will be zero. But the time takes it past that to hit the teacher in the face. So this little distance down in here is in fact the vertical displacement of the sponge at that particular time, which is minus 0.30 metres, which means 0.30 metres down from where it started from. But the question asks us to find the height above the ground. Now we know that the height above the ground where it was launched was 1.5 metres. So the height in which sponge hits the teacher is just simply equal to 1.5 metres take away 0.30 metres. So that height is 1.2 metres above the ground. If you look at the diagram, you can see this distance here is going to be 1.5 metres. The sponge has come down a distance of 0.30 metres, which leaves a distance from here to there, which is the height above the ground, of 1.2 metres. Question 1, Part B. The student throwing the sponge makes the following statement. If the sponge is thrown with a higher speed at the same angle from the same height, then it would take a shorter time to hit the teacher in the same place. Explain why the student's statement is incorrect. Now, to answer this question, we're going to take you over to the PHET site where they have a simulation for a projectile. It's an amazing site and you can learn a lot about these phrases just by experimenting with this site. Okay, let's go over. Okay, here we are at the PHET simulation site on the projectile page. Now you can see I've set up the projectile to be as near as possible to the SQA question. I can't use a sponge, but I can use a cannonball, and I have a height of 2 metres rather than 1.5. But what we're going to try and do is to launch the projectile at a certain speed, initial speed of 10 metres per second at an angle of 30 degrees. And then we're going to increase that speed and see the different paths of projectile and compare it with how, in fact, the teacher is sitting. So let's launch the projectile first of all at 10 metres per second. Now you can see it slaps bang right into the teacher's face at 10 metres per second. Now if I increase that speed to 15 metres per second and launch it again, watch the different projectile motion. You can see it completely misses the teacher. It's much higher and it travels much further. Now let's put all the physics together and prove that the student's statement is incorrect. And it starts off with launching the sponge with a higher speed at the same angle. So what will this result in? It will result in a larger horizontal and vertical components of the velocity. And you can check that out from the diagram there. Now, a larger vertical component of velocity means that the projectile will take a longer time to reach its maximum height, because acceleration needs a longer time to reduce the initial velocity to zero. And remember, at the maximum height, the velocity is zero. The next part is the maximum height will then be higher. And finally, the increase in overall time by increasing the launch speed will result in the projectile travelling further because it's having a bigger horizontal component and a longer time, and therefore it will travel further, as can be seen from the diagram. So if you actually increase the launch speed at the same angle with that sponge, it will sail higher over the teacher and land further away from her, and she'll not be soaked.